Welcome friends. So the first step when you are planning to do the release setting calculations for a transformer differential production is to collect the data regarding a transformer. So here you can see that we are doing the setting calculations for 100 MVA power transformer. So this is an 100 MVA transformer. So the transformer of 100 MVA is a really big transformer and is being used at the transmission level. So normally at the distribution level, you will see 500 kVA, 1 MVA or 2 MVA transformers. But the transmission level, the capacity of transformer is quite big. So 100 MVA is our transformer rating. Next is the voltage level. So the voltage level of the transformer at the HV side is 132 kV. So HV side is 132 kV voltage, and the LV side voltage is 33 kV volts. So we know that the transformer MVA will remain same at the HV and LV side. So both the HV and LV side of the transformer should have the same MVA. So we know that the MVA formula is equal to, or you can see MVA or S is equal to under root 3 V into I. So because S has to remain constant, that is 100 MVA, then under root 3 V into I. So if the voltage is increased at the high voltage side, it means that the current at the high voltage side is less. So V is high and the current is less at the high voltage side. That is 132 kV is the voltage level, and at 33 kV the voltage is lesser as compared to the high voltage side, and the current will be at the higher side. So it means that even at the balance condition, even everything is fine, there is no fault, there will be a difference of current between HV and LV windings. So there will be difference between HV and LV windings. So the I, it means that IHV in the balance condition will not be equal to ILV. It is because of the transformer at transformation ratio. So we need to compensate this difference in our relay. So we know that KCL is stating that current in at a given node is equal to current out. So the current in is equal to current out, but this is not applicable to the transformer, because in the transformer, because of transformation ratio, the current in, for example, it could be at high voltage side 1 amps and the LV side could be 2 amps if it is, for example, 2:1 transformer. So voltage is reduced 50%, current is again increased by 100%. So voltage is reduced by 100% and the current is also increased by 100%. So that's why we need to compensate this difference. And the modern numerical relays, you just need to you need to select the vector group correctly in the numerical relays in order to compensate this difference of current. Second is a vector group. So you can see it is Y and D1. So one thing you can notice that the HV side is shown in the capital letters and the LV side is shown in the small letters. So this is another important thing to know, that during a vector group, when you are writing the vector group, you should also consider the HV and LV sides. So you can see here that HV side is basically connected in star. So HV side is connected in star and the LV side is connected in the delta, and the neutral is grounded. It's not mentioned here. So neutral is grounded, so it is a star delta transformer. And 1 here is indicating that if you know the clock method, so the clock is divided, we know that, into the 12 equal parts starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's divided into 11 equal parts, which means that the phase shift between HV and LV1 means, here you can see it is showing 30 degree. So it means that the LV winding is lagging 30 degrees. 1 into 30, it means it is a phase shift of 30 degrees between HV and LV voltages. and also similarly for the currents as well. So there will be a phase shift of 30 degrees between two windings. So even the you can see that the system is balanced and healthy, even we compensate the magnitude difference, the transformation difference, if I even I compensate, but because of the phase shift, there is a possibility of differential current flowing into the relay. So this is another thing that we need to compensate in our differential relay setting calculations. So for example, if you have one current, this is a one current which is 1 ampere at HV side, and considering a 1:1 transformer, for example, there is no difference in the magnitude of the current in the healthy condition, and but there is a phase shift of 30 degrees. So this is LV. So here you can see this is HV, and this one is an LV current. So this is an HV current and this is an LV current, and here you can see there is a phase shift of 30 degrees between HV and LV. So if you make the differential current of these two, you have to subtract IHV minus ILV. So if both have same phase angle, both are at the same phase angle, the value has to be 0. But if there is a phase shift of 30 degrees, if you differentiate it, you have to make it minus. So I will take this one to this side here on the top. I have to make it minus. So it means that now, okay, let me draw into a separate sheet here. Okay, so consider the fact that we have HV current 1 amp and LV current 1 amp, but 30 degree lagging, because now we have a phase shift. We are considering a transformer that is 1:1 transformer. Okay, so there is a shift of 30 degrees. If you want to calculate differential current, so this is IHV and this is ILV. So if you want to calculate the differential current, you have to make minus. So IHV minus ILV. So you want to make it minus, then you just need to change the direction of the current here. So here you can see this is ILV minus. So now you sum these two, IHV and ILV minus, the sum will be, you can see this differential current will be that much huge. So if you have just use head to tail rule, add this LV and IHV. So I take IHV here, use head to tail rule. So here you can see you will get this much of differential current. I differential, even everything is fine and system is healthy. So if you consider a case of 1:1 transformer, again this is the case of 30 degree phase shift, and you consider the case of 0 degree phase shift. If I draw, this is IHV, again IHV is equal to ILV, as we assume 1:1 transformer. So ILV will be also at the same position. So IHV and LV both are in same direction. So if you want to make a differential, you just need to make it in minus direction, ILV. So this is minus ILV. So if you combine these two equal and opposite forces, the sum of differential will be 0. So it means that because of phase shift, differential current will be produced. So if you use, you can also use a symmetrical components or the polar method to calculate the differential current if you are not compensating in the transformer, then how much it will be coming. So simply here you can see this is a vector group and we have to compensate in using our setting calculations. So next item here you can see is the percentage impedance of the transformer. So this is a 12.5% is the percentage impedance of the transformer. So the percentage impedance of the transformer is important to basically compensate or to limit the fault current. So whenever there is a fault current at the transformer, the fault current is limited by the percentage impedance of the transformer. So if I make an equivalent circuit for the transformer, so you can see simply this is the percentage impedance and this is the ground fault. It means that this is the voltage here. So simply the fault current will be limited by the percentage impedance of the transformer. So higher is the percentage impedance, lower will be the fault current. So this is 12.5%. So I will explain separately in the next video the relationship of percentage impedance, the relationship of short circuit MVA, and what is the meaning of percentage impedance. This is percentage impedance is a special impedance that is measured in the voltage or in the per unit values. This is not measured in ohms. So we will see why it's done and how this is being measured, which method you are using to measure it. So we'll discuss this in a separate next lecture. So here you can see this is the HV side current. So in the next lecture also we will calculate how this HV side current is calculated, and the LV side current is shown here, which is 1749.5 amps. So you can see there's a difference between HV and LV currents. This is called as full load amperes. We are calling it FLA, full load currents or full load amperes. So this is the maximum current a transformer can supply, or transformer can be put loaded up to this amps plus the overload if it is allowed. So next you can see the tap change range. So this is plus minus 10%. And why we are considering a tap change range in our differential calculation? It is because whenever you are changing the taps, it means that you are now changing the voltage ratios V1 or V2, or you are also changing the current ratios I2 by I1. So it means that you are changing transformation ratio. So it means that if you put a factor in a setting calculations that this is a factor of SB to LV, still there will be an error, and this error will be introduced by this additional tap findings, because the ratio will not remain uniform. At different taps ratio will be different. So we will see how we have to compensate this ratio as well, how to compensate the ratio, tap change ratio in our setting calculations we will see as well. So next is the primary current CT ratio. So this is at the primary side, because the current is less, so the CT ratio has been chosen as 500 by 1, and the secondary side CT ratio is chosen as 1800 by 1. So these are the CT ratios that has been chosen. So this is the primary CT ratio 500 by 1, and it's a secondary ratio 1800 by 1. So we have to also use these CT ratios in our calculations. So this is all about the transformer and CT details that we will use to do our calculations. And I hope you like this lecture, and in next lectures we will continue in explaining how to calculate the relay setting and calculations, and also we will see some concepts of percentage impedance, fault, short circuit MV, and how to calculate the relationship between these two, full load currents. Thank you very much.